Thanks for coming to this AgTAC seminar. Just before we start, I want to acknowledge the Aboriginal people and Torres Strait people as the first inhabitants of the nation, and acknowledge traditional custodians of the Aboriginal lands where our staff and students live, love, learn and work. So, before we carry on, today we will be hearing from Professor Paul Nelson. Paul is a soil scientist here at JCU working in the agricultural environmental interface. He has accumulated experience in the coldest to the hottest and driest to the wettest agricultural environments on Earth, and has delved into the worst and best soils. I'm curious to know how he's judging the soils too. One of his main interests is in carbon cycling, with soil being one of the biggest terrestrial stores of carbon and the biggest terrestrial source of atmospheric CO2. So what interests him most is how to manage agricultural land well, and presumably how that then affects carbon storage. So today Paul is going to talk to us about how a new technology called enhanced rock weathering could help in the goal to reach net zero greenhouse gas emissions. So how effective is it, and how does it change depending on the environment? So I'll hand it over to Paul, and if you could please just hold your questions to the end, and then we'll have a short Q&A once he has done his presentation. Thank you.
Thanks a lot, Adam. Okay, so that's what I'm going to be talking about, enhanced rock weathering for carbon dioxide capture. So what it is, the state of research globally, and our contributions to that. Fred, Hannah and Carla have done most of the work that I'm going to be talking about, and there have been a variety of important partners that have contributed. So the first five here have provided the funding for the research. The University of Sheffield hosts the Leverhulme Centre for Climate Change Mitigation, and we're part of that, and they provided most of the funding for most of the work we've done to date. Consolidated Pastoral Company, they're a large Australian beef producer and landowner, and we're working with them. Undo Carbon are a large enhanced weathering project management company. They're based in the UK with operations globally. SRA are the Australian Sugar Industries Research and Development Corporation, and the Australian Government, through the Climate Smart Agriculture Program under the Natural Heritage Trust, are funding a large new program of research that we've started in collaboration with these three organisations: the University of South Australia, Tropical North Queensland Drought Hub, and Carbonaut, who are an Australian enhanced weathering project management company. Okay, so lots of other people have contributed as well, and many of them have done really hard physical work in terrible conditions. So thank you very much to all these people who've contributed to what I'm going to be talking about. I'll start off by describing enhanced weathering, and then I'll describe the journey we've taken at JCU. So what is it? Why should we be interested? I'll talk about the first enhanced weathering field trial in Australia, which also happens to be one of the first in the world. The work we've done testing different feedstocks for enhanced weathering, and where we are now and where we're heading. We have this human-generated global scale problem of producing too much carbon dioxide and other greenhouse gases. This is about where we're at now in the amount of emissions, so the bluish colour being carbon dioxide and deforestation from various human activities, and the pink being non-CO2 greenhouse gases. And this is where we've committed to get to by 2050, the dotted line being net zero carbon dioxide emissions. Now, it's recognised that it won't be possible to get carbon dioxide and other greenhouse gas emissions to zero by then, so we need removals to get the net emissions to zero. And you can see here that the net emissions we need are about 10 gigatons of carbon dioxide equivalent per year. You can see here that the removals, or carbon dioxide removal, CDR, are classified here as either conventional or novel, and enhanced weathering is considered a novel CDR removal technology. So let's start by defining it. Over the last 50 years or so, we've come to understand the importance of rock weathering for carbon dioxide removal globally. So what happens is that carbon dioxide dissolves in water to form carbonic acid. And so, for example, rainfall is slightly acidic because it dissolves some of the carbon dioxide in the air. And that carbonic acid reacts with silicate rocks. So most rocks are silicates, so they're made up of silicon and oxygen mostly. And that carbonic acid reacts with them, weathers them, so breaks them down. And one of the products of that reaction is bicarbonate. And bicarbonate is a solute, it's an anion, and it leaches through the soil to the groundwater and rivers and the sea, where it can remain as bicarbonate. There's a lot of it in the ocean, or it can precipitate out as carbonate or limestone. And this sequence of events is what's taken most of the carbon dioxide out of the atmosphere. The early Earth had an atmosphere dominated by carbon dioxide, and now most of the carbon on Earth is in the form of limestone due to this process. So about 20 years ago, the idea of enhanced weathering came up. Perhaps we can accelerate weathering sufficiently to make a significant contribution to the intentional removal of carbon dioxide. So how would we do that? We'd take a weatherable rock that's rich in magnesium and calcium, and we'd crush it. And so basalt is a good example of that, and apply it to land. The high carbon dioxide concentration in the soil due to the respiration of roots and microorganisms and so on, and the moist conditions accelerate the weathering. So that's the idea, and you can see it in the diagram here where you've got the mining of the basalt, the crushing of it, transport, spreading on the field, and then here we've got a field with carbon dioxide going in, being absorbed by photosynthesis, coming out, being produced by respiration, and we want that out arrow to be smaller than the in arrow so that we're capturing carbon dioxide. Here, what's happening in the soil is blown up, so we've got the crushed basalt here, and basalt is essentially oxides of silicon and other metals like magnesium and iron. So that's our basalt, and it's reacting with the carbon dioxide and water to produce some new minerals, some secondary minerals, release some nutrients like magnesium in this case, and produce bicarbonate, which then can move through the groundwater, through the rivers and into the sea. So that process you can, for those who are interested in the chemical reaction, this is what it looks like. So if we take a simple silicate rich in magnesium, in this case, react it with carbon dioxide and water, we get the bicarbonate, magnesium is released, and we get silicic acid, so another type of mineral formed. So this idea is attractive because all the technology already exists to be able to do it, and there's plenty of accessible agricultural land where we can do it. So if the amount and value of the carbon dioxide removed exceeds the amount of carbon dioxide emitted and the cost incurred of doing it, then it's worthwhile. So the next question is, how does enhanced weathering stack up against the other potential carbon dioxide removal technologies? Here we've got a list of them, from afforestation and reforestation up the top, and that's pretty straightforward. You know, that's where you have land that didn't have forest or they've been cleared before, and we grow forest, and that captures carbon in the biomass. Down to a more drastic and less well understood and less extensively practiced one, which is direct ocean carbon capture and storage, where we take carbon dioxide, either dissolve it or compress it, and we pump it underground into geological formations and store it there. And that's being done in Iceland at the moment. And there's a whole range of other ones in between. So enhanced rock weathering, you can see it in the middle here. It's considered a geological capture process rather than biological. It's considered novel rather than conventional. It's got a pretty low readiness, so light blue compared to these ones, darker blue. It's got a high mitigation potential and a good storage timescale. So because it's not so ready, but it has high potential, there's a clear need for research. It's also worth just quickly comparing it to soil carbon sequestration as organic carbon, because that's in the conventional category and it's already being done for that purpose. And so that's ready, it's happening. It's got a good mitigation potential. But one of the disadvantages is that it's a bit vulnerable. So if you stop the practices that are increasing carbon, then you can lose it again. Or if the climate changes, you can lose it. And so it's that is a disadvantage as So I've been talking solely about carbon dioxide removal so far, but it's also important to consider the soils to which we're adding the rock. And we need to maintain or improve their health or their condition. So some of the main degradation processes that we need to counter are things like acidification, organic matter decline, nutrient decline, and so on. Australian soils generally are quite poor, inherently poor, and that's largely because they're highly weathered, very old. And so to maintain or improve them, it requires effort. It requires inputs or costs or skills or knowledge to actually improve the situation. Now, crushed basalt has a number of benefits. It has a liming effect, so it raises the pH of soils, and many agricultural soils are acidic, and we do already lime them. When we lime them with conventional agricultural lime, which is limestone, you actually get emission of carbon dioxide, whereas when you apply a silicate rock and it weathers, you don't get emission of carbon dioxide, so that's one advantage. When you raise the pH, you also get less nitrous oxide emission. That's an important greenhouse gas, so that's another advantage. When the weathering happens, you get release of nutrients, and I've spoken about some of those, but there's more that are important nutrients, essential nutrients for plants. You get new clay minerals that form, and clay minerals are part of what contributes to soil fertility, soil quality, so that's useful. And potentially, due to these things, you can get the capacity of the soil to retain soil organic matter or soil organic carbon can also be increased, so that's also useful for its soil health benefits and for carbon capture. Now, these benefits have been known for quite a long time, and there are already farmers who are applying crushed basalt and other similar rocks for these reasons. Now, some good research was done in JCU on that 25 years ago, led by Ross Coventry at JCU and Gavin Gilman at CSIRO in Townsville. And they did a series of pot trials and lab experiments that quantified these benefits. And they were using a crushed basalt from Innisfail, which is the trade name Minplus. It's a finely crushed basalt, which is still available for sale for that reason. It's a lava flow at Innisfail. The other thing reason I put this up is that I like the term rejuvenating, because it's essentially what we're doing is making these soils younger by applying minerals that have been weathered out of the soil. So we're sort of reversing that aging process to some extent. So generally speaking, in most situations, applying crushed basalt is good for soil. So summarising the enhanced weathering idea, it's got quite a few attractions relative to other negative emission technologies. The rock, for example, basalt's abundant and widespread. Here you can see in Australia, it's widespread throughout the main agricultural areas, and that holds through much of the world, actually. The basalt is quite common in many agricultural areas. It's actually a waste product of quarrying and mining. So when companies quarry to produce aggregate for concrete and so on and roads, they have this fine material, which is crusher dust. It's a waste product. It's not worth much. And a lot of mines produce it as overburden. So it's already available as a waste product. The land, the technology, and the infrastructure are all available. So it's spreading basalt's analogous to spreading lime, which we do quite a lot of already. There are the co-benefits, which I mentioned. Now, there are also potential detrimental effects. So, for example, you can get contamination if you use the wrong type of rock. You can get compaction from putting all this other material on. If we scale up to what we needed, we're talking about roughly a doubling of mining activity. So there are lots of downsides, like there are to everything. What do we know? So we know that the hotter and wetter the climate, the better. The more biological activity, the better. And the higher the calcium magnesium content of the rock and the finer the grind of the rock, the better. What we don't know, what are the actual benefits and costs in the field? There's been very little field experimentation that's happened to date. It's starting to come in, but not much yet. And also, how does that vary across different soils and cropping systems, etc.? Now, the other thing that I need to mention is the scaling up aspect. So from the first graph I showed you, I said we need 10 gigatons of carbon dioxide equivalent per year drawn down. So that's 10,000 megatons or million tons. And I've changed the units because of this graph here, which I'll come back to. So we need around about 10,000 megatons of CO2 per year carbon dioxide removal. Now, modelling has suggested that enhanced weathering could contribute about 2,000, in the order of 2,000 megatons. So that's really quite significant, chunk of that. So that looks very interesting. Let's go to this graph now. So here we've got dates across the bottom. So this is the recent years. And here we've got the megatons per year in carbon dioxide removal technologies that are in place already. You can see that the big ones here are BECCS, which is where you grow a bioenergy crop and you harvest it and you burn it for energy and you capture the carbon dioxide. Biochar is another one that's quite big and increasing. Direct air carbon capture and storage, which you probably hear a lot about, where you actually suck the carbon dioxide out of the air. It's sort of not showing yet on the graph. And enhanced rock weathering is just starting to show on the graph. So the last point I want to make about this graph is this is less than 1.4 and we need to get to 10,000. So that gives you an idea of the scale. But this 2,000 is significant, and that modelling sort of pricked up the ears of a lot of people, and it's led to the rapid expansion of a multi-million-dollar industry over the last 6 years or so to do it. So about a week ago, I counted over 18 companies that are managing enhanced weathering products around the world, and over 8 companies that are auditing, certifying, or helping quantify carbon dioxide removal via enhanced weathering. And that commercial interest, it comes from the fact that the product, which is carbon credits, is desired by corporate carbon dioxide emitters, and selling the product might provide an income for farmers, mine and quarry operators, and all these enhanced weathering project managers and brokers and auditors and lawyers and so on. So a whole new industry. Now on to our research. So in 2016, David Beerling at the University of Sheffield initiated and established the Leverhulme Centre for Climate Change Mitigation. And he approached us because they wanted a trial in the tropics where the conditions for CDR, for carbon dioxide removal, should be ideal. So we joined up with the centre and we started a field trial. We found a good sugarcane farmer down at Gordonvale. We found a nice field in his paddock which had highly uniform, permeable soils. And it's hard to find a good field soil, by the way, with the field site with uniform soils. And we started this field experiment where we're adding 0 or 20 or 50 tonnes of basalt per hectare per year since 2018. So these are the plots here. They're 6 rows wide. They're 500 metres long, so we could get a commercial cane yield harvest figure for them. And we're measuring, taking detailed measurements at this end of the field. So this is the crusher dust that's been delivered at that site in one of the years, and we're loading it here onto the spreader, which is a computer and GPS controlled spreader that puts exactly the rate we want on exactly the area we want. And then we measure the carbon balance. So we measure the bicarbonate leaching through the soil, and we do that below the root zone because everything's happening in the root zone. The carbon dioxide is being produced, the weathering reactions are happening, etc. So we want to be below that to get the net effect of that as the solutes leach down. So we capture the leachate in these devices, which we bury in the ground. The top of them is a metre below the surface. And we sample that leachate and measure the volume and concentration. We also sample the soil and analyse it every year, and we sample the cane and analyse it every year. Now, it took us a few years to get some of these techniques right because there wasn't a precedent or a manual for this sort of experiment at the time we started. But by the 2022-23 wet season, we had the technique sorted and we got our first solid year of data. What we found was that there was significant weathering. We measured significant weathering of the basalt because there was an increase in soil pH, there was a release of magnesium, but we got negligible carbon dioxide removal. So moving to the graph that shows that data, here's the date during the wet season. Here we've got the cumulative rainfall, which is this blue line, and the cumulative leaching with the daily rainfall shown here. The difference there is the evapotranspiration loss, that's the water going back up through the cane. On this axis, we've got the bicarbonate leached, and the orange line is the 0 basalt plot, and the purple line is the 50 tonne per hectare plot. So you can see the 50 tonne per hectare plot is slightly higher, but when we look at the difference, so this is the carbon dioxide removal due to enhanced weathering, that figure of 0.61 kilomoles per hectare is equivalent to 0.026 tonnes of carbon dioxide per hectare per year. Now that compares to a figure from the mid-US where they estimated 2.6 tonnes of carbon dioxide per hectare per year. So we are measuring about 100 times less. Now this was pretty disappointing because we thought we had the ideal conditions for carbon dioxide removal. So the question is, what's going on? So we did some more analysis and we worked out why. Now it turns out that only a small proportion of the weatherings, this weathering that's going on, was due to carbonic acid weathering, which is leading to carbon dioxide removal. Most of the weathering was done by stronger acids than carbonic acid, which are present in this acidic tropical soil. So that explained the low carbon dioxide removal in our trial. It also helped explain why a levercume trial in Malaysia had reported a year earlier had also produced similar negligible effect. So this pH effect is pretty important. And putting it all together, all the information from our work and from other people's work, we came up with this generalisation where we've got 4 soil pH profiles here that are typical of the range from wet climates to dry climates. So in wet climates, you typically get sort of slightly acidic topsoil and more acidic subsoil. In dry climates, you typically get sort of neutral, range of neutral topsoil and more alkaline subsoil. And in these soils, we're not getting carbon dioxide captured during enhanced weathering. Sorry, this grey area shows when you add the silicate rock, you're getting an increase in pH due to the weathering. The increase is greater in the acidic soils, but you're not getting that translated to carbon dioxide removal. Whereas in these soils, you are getting carbon dioxide removal. And in this case, it's moving as bicarbonate through leaching through the profile. In this case, it's probably accumulating as carbonate within the soil rather than in the ocean. And this concept is really important because quite a few of the modelling studies in the past have assumed that carbon dioxide removal was higher in more acidic soils. Now, this concept's been backed up by geochemical modelling we've done that takes the basalt and soil properties into account. So Hannah Green modelled the weathering of basalt applied at 100 tonnes per hectare over 15 years and calculated the cumulative carbon dioxide removal. And here you can see some of the results of that modelling at 3 different pHs. And you can see that there's this dramatic effect of over 15 years, the amount of carbon dioxide that's removed by the basalt weathering due to pH. And the other interesting thing about this is that these figures are actually of the same order of magnitude as what we've measured in the field. So this modelling backs up what we're finding in the field. So while I've got this slide up, I'll also introduce the main point of Hannah's PhD research, which is to assess the effectiveness of sugar mill ash for carbon dioxide removal via weathering. And I'm going to do that by adding a few lines to this graph. So mill ash is a fine alkaline product that may capture carbon dioxide as it weathers in a similar way to the silicate rocks that I've been talking about. And the modelling indicates that indeed it does appear effective, with most of the weathering happening in the first 5 years. And that's handy because that's the length of a typical sugarcane crop cycle. So you could add it, let your crop cycle go for 5 years, and then when you plough out, you could add it again and incorporate it. So these numbers, the different mill ashes, they're lower than the basalt, but this was 100 wet tonnes and it's about 50% water. So you can pretty much double these amounts if you want to get a comparable effect with basalt. So it's really quite significant and interesting. So Hannah's work using the results of this modelling and also field and laboratory experiments she's doing to work out the potential benefits of mill byproducts for improving soil and capturing carbon. So that brings us to where we are now. So the effects of climate and rock type are now pretty well understood. So now we're focusing on soil and agricultural system effects. So that's the first question there. The second question is, how can we monitor this carbon dioxide removal in commercial projects in the field? And that question is really an urgent need for regulators and for enhanced weathering project management companies. There are 3 new projects we've started this year and last year. In the first one, so that tackles this. We know that soil conditions are important, but to what extent could we increase carbon dioxide removal by manipulating these conditions in a conducive climate like the wet tropics? So we've established a field trial here on Cairns campus together with Undo Carbon. And the second new project, tropical savannas constitute a vast area with ideal conditions for weathering for part of the year, not all of the year, but during the wet season it is. So we've started a field trial together with consolidated pastoral companies on one of their stations to the west of Cairns. Lastly, we are leading a consortium of partners, the partners here, which is funded by the Australian government, in which we're about to set up 7 new field trials in a range of farming systems throughout Eastern Australia, quite a big program. So while this field and lab work is ramping up, the Leverhulme Centre is doing a desktop study assessing scenarios for implementation of enhanced weathering across Australia, and several other Australian groups and universities and in CSIRO are doing good enhanced weathering research as well. So we're all part of a large and rapidly expanding research effort throughout the world. Which brings me to my summary. So enhanced weathering has substantial promise as a carbon dioxide removal technique with co-benefits. Sugar mill ash may be more effective than basalt in some places, especially near sugar mills. Soil properties are important, and acidity limits carbon dioxide removal. It's an important finding which is having implications for the way it's done. And the goal now is to identify the sweet spots for maximising benefits. And lastly, I'd just like to say that while carbon dioxide removal research is important and needs to be done, we shouldn't let it distract us from the more important job of reducing emissions. I think that's worth saying. So that's it. Thank you.
Thanks, Paul. Really interesting talk there. So yeah, no, I've definitely got some questions, but before I ask some, is there anybody in the audience here listening with some questions? Just raise your hand if you do. Bronson.
Yeah, thanks. Really interesting presentation. I really liked the story of, how you ran through the history of, how you got to this point. I'm interested in your question about, how to do the monitoring in a cost-effective manner. So I understand you said that the way you did it for the research was you were looking at the groundwater, so kind of underneath the crop, basically the water that's kind of coming down as kind of deep drainage down into the soil. Is that the only mechanism? I'm just sort of curious about what are your thoughts on, how to approach that monitoring kind of question?
Yeah, that's really important. So what we're doing in research is just not cost effective commercially. So we're measuring in the water, but we're also measuring in the soil. So they're the two components, and depending on the climate, one might be more important than the other. A lot of people working on this issue, and the way it's being approached and the way it's probably going to pan out to be most effective is to do a combination of measurements and modelling. So at the moment, people are measuring soil characteristics and using modelling to calculate the carbon dioxide removal. And that's probably going to be the most effective way, because you can measure soil properties quite easily, every year. So that's the way it's heading.
Yeah, thanks. I guess that puts a lot of faith in the accuracy of the model, though. Indeed. Particularly if there's a lot of money out there, right? Like this is potentially, a lot of money, to be made in terms of selling carbon credits. So
yep,
you have to trust them. You have to really trust the model.
Yep, that's right. A lot of people are putting their brains to that problem, and you're right.
Yep. Yeah, thanks.
Thanks, Bronson. Yvette?
Yeah, just another question also on the modelling, Paul. What are the models that are being used here, like you said that Hannah was doing some modelling, and then you were talking to Bronson about also using another model to validate or estimate the carbon dioxide removal. What are those models?
Yeah, so they're all essentially reactive transport models. So they look at the geochemistry of the reactions and the water balance and so on. So the one Hannah's using was one that was developed by others in the Leverhulme Centre. So she's used the identical model, and it's based on Freak C, which some people might know, a geochemistry model that's widely used, an open source model. Other people have got their own models, but they're all essentially the same thing. They're all geochemical reactive transport models.
And how do those models differ from APSIM?
So APSIM doesn't do any of that geochemistry modelling, and we actually applied to ARC to link that sort of modelling to APSIM. We didn't actually get that grant, but hopefully in the future we'll. So
yeah.
It would be really useful to link these geochemical models to a crop system model, and that's something that isn't really done yet, but that'd be a great thing to do.
Yeah, you're collecting a lot of data to make that feasible, and now it might be more palatable given the importance of the enhanced weathering process.
Yeah, it's definitely a logical step forward, definitely.
Yeah. Thanks, Paul.
Thanks, Yvette. We'll do one more from Christopher.
Chris, yep. Paul, I noticed in the aerial photo of the cane on Cairns campus, there visually seems to be some difference in treatments there. I'm wondering if you'd like to comment on those.
Yeah, sure. You can see there's 6 replicates, and you can see those visually, and they're actually it's actually a cane variety effect that you can see. So we couldn't get all one variety, so some of the reps have got different variety, and that's what you can see in the colour and vigorousness of the cane. Yeah, I was surprised how big the variety effect is, to tell you the truth, but anyway, it's blocked out in the replicates.
Thank you. Cheers.
Mind you, we can actually see a treatment effect, I should say, actually. So it just wasn't visible in that slide, but we are seeing a treatment effect. So we're doing treatments to enhance the carbon dioxide production. So we're adding mulch and adding more fertiliser to some, and you can see effect of the treatments already. So
very good. Cheers.
All right. So we'll go with Mahmood, and then we'll hand it back to Yvette to wrap it up.
Thanks, David. Thank you, Paul. That was a great presentation. I'm interested in the groundwater side of things. So that bicarbonate that leaches into the groundwater system, is there an understanding of how much groundwater is basically transporting that bicarbonate into the drains potentially? And if the conditions are acidic, does that bicarbonate then turn into CO2 and go back into the atmosphere? So what's the fate of the carbon after it's been absorbed? Is there an understanding of that?
Yeah, another really good question, and something that is being tackled but needs a lot more research. So yes, you're right. If that bicarbonate meets acidic conditions on its path, it'll be lost again. If it meets alkaline conditions, it'll be safe and might even increase. And that's an area that our group is not directly working on now, but we're certainly working with people who are. So, for example, Clem Duverne, CDU, he looks at carbonate rivers, the inorganic carbon. There's groups elsewhere in the world that are looking at that. But yeah, it's a really important question that we need more information on.
Yeah.
So it doesn't always say in drier climates it'll accumulate in the soil, so that's not an issue in drier climates. But in wetter climates, yeah, that's important.
Yeah, okay. Thank you.
Okay, Yvette, I think you had some final comments you want to do.
Yeah. I would also like to thank Paul for the presentation, and it was a wonderful story as well, in that it made it easy for people like myself who don't have that background in soils to follow along. But just a couple of things. I sent an email around a few days ago about the Trop Ag 2025 conference, which will be held in Brisbane. It's organised by UQ, and Jenny Seddon has paid some money for JCU to be a silver sponsor at that. So Jenny's hoping that we can get some attendance, some JCU representation there. She is really wanting to send the message that we are doing agricultural work at James Cook Uni. So really pleased to have her support. And if you are interested in going to the TropAg conference, please, if you could send me your email by the 7th of, send me your abstract by the 7th of April. And we're going to try and give some funding to help support some people who don't have the funds to get there. But if you do have the funds and you are wanting to go on your own, if you could just flick us an email as well, it will just help our research office coordinate with UQ on that. So that's the first thing. Is there any questions on the TropAg conference? The next thing is we're just going to have an informal coffee break on Tuesday, the 8th of April at 9 o'clock in the Science Place. So apologies for the people in Cairns, but I promise that we'll have a coffee break next time I'm up in Cairns. So that'll be on the house. And I've managed to talk UniSuper into footing the coffee bill for us, so it won't come out of our AgTAC purse. Yep, I'll send an email around about that as well. And we've got the away day on the 15th of May, which Di has sent out a calendar invite for. So because we're going through this restructuring phase within AgTAC 2.0, we've nutted out what our key focus areas are. I want to use that away day, as always, to give our early career researchers and our PhD students and master's students an opportunity to speak about their research. But instead of having the senior researchers also give their 3-minute presentation, we're really looking to have a significant part of the away day looking at what are the challenges and opportunities for AgTAC 2.0 and establishing our pathway forward. So within the restructure, I outlined when we had our town hall meeting that we are going to set up these we'll have task teams, which will be an agile way to tackle things that are important for us to pursue. So the new structuring will make it more easier for us to, go forward with ideas, because often we've come up with, somebody's had a great idea, like Adam, you've said, oh, wouldn't it be good if we had some micro-credentialing? But we just need some champions, to try and carry that forth. So that's just a bit about the away day. And our next speaker, Di, did you want to talk to that? It's been organised by George Van Vunis. George is a chemist working with Yang's team here in Townsville, and it's an industry rep that George has been working with. So Di, did you have any more details to share about that? Just unmute, Di.
Yes, no, we haven't received an abstract, but it's on Biogene Technology, and it's going to be on the 8th of May at 2 p.m. So we will, once I get some information from Peter, I will share that with everyone in an invitation, so you've got the details of that.
Yeah, and if anyone does have any other external colleagues that they would like to invite for a seminar, please let Di know. Yes, Bob.
Yvette, just on the TropAg story, the Crawford Fund offers enrollment in the conference for postgraduate students from developing countries, and we give preference to students located outside of Brisbane. So obviously that's relevant to JCU students located in Townsville and Cairns. So I'll just mention that if you've got postgrad students, they have to be from a developing country because of that's the focus of Crawford Fund support. They'll still need to find their own travel and accommodation support.
Yeah, thanks for that, Bob. So are you saying that the Crawford Foundation would be able to pay for the registration fee for students from a developing country if their application was successful?
Yes.
Yeah.
So they get full registration and also they're guests of the Queensland Committee at the conference dinner.
Oh, okay. Well, that's a wonderful opportunity for students. So I'll try and promote that as well. But before we, sorry, Bob, go.
Yes. If they check out the TropAg website, the information is there, eligibility criteria, things like that.
No, terrific. Thank you very much, Bob, for bringing that to our attention. Before we go, could we just have the cameras on and we can get a selfie? And on the count of 3, 1. Oh, we've still got a few coming. Okay, that might be it. On the count of 3, smile. 1, 2, 3. Excellent. Thank you very much. Okay, that's a wrap, everyone. Have a nice day. Thanks for coming. See ya.
Thank you.
Thanks all. Thanks, Paul.
Bye.
Thanks. Bye.
Thank you.